atlas is either great, thanks. Either, I mean, great for the recording, I mean. So either we're based on anatomical criteria or even functional. So we have brain atlases and we can split the brain into different regions. And then with the DTI, we can reconstruct the connections. And therefore, we form a brain network from the data of a specific individual. And then, as we said, we simulate and we produce different kinds of neuroimaging or functional data, for all of which we also know the source activity, actually. We know exactly what is the activity of the brain that generates this, because this is virtual activity, artificial one. So these are kind of the inputs of the model, and this is kind of the outputs of the model. And what gives real life to the model is the fact that this brain network has some specific dynamics allocated in each one of these nodes that form this brain network. This dynamics is usually some kind of low-dimensional dynamics we describe with a few differential equations, like you see in the example of the very well-known Wilson-Cowan model. These equations are called neural mass or mean field models. The reason is that the state variables of these differential equations describe the average dynamics of neural populations. So it's a kind of approximative dynamics, the dynamics of millions of neurons usually that reside in one brain region are described by only a few dimensions in these approximations. For instance, in this case, the Wilson-Cowan model is comprised by two state variables, each one of which describes the average dynamics, for instance, the kind of synaptic activity or firing rate of a population, excitatory one and an inhibitor one. And these two populations are coupled by self-excitation and by also excitatory and inhibitory connections between them. So such a model is placed at every one of the nodes of the network, and then the connections we showed before form the whole brain model. And this then gives rise to the global equation of TVB, where all the elements come together. As we said, it's a system of differential equations in the end of the day. The most important part is the specific dynamics we place at every node, the neural mass model. The state variables describe average dynamics of the populations like firing rates, field potentials, etc. There is a global coupling between brain regions, which depends on the structural connectivity weights and time delays that we recover from DTI. And in cases where we do a more detailed simulation on the surface of the brain with many more nodes, then we can also have a local connectivity kernel. Plus any other inputs like stimulation, when we model stimulation of the brain, for instance, and of course noise, because we don't model all details of the brain. There is a lot of noise also that, or randomness, in other words. Now, what I want you to notice here is that this is a very homogeneous equation, which means that we practically have the same kind of dynamics all over the brain tissue. This is this has to do a little bit with the history of this kind of models that comes from neural field theory, where the physicists that work in neuroscience make the assumption that the brain cortex is like a sheet of neurons that is more or less homogeneous. It's true, of course, that we can have different parameters at different regions of the brain, but still the kind of dynamics is quite the same. This does not allow us, in principle, to study specific systems that have an intriguing circuitry that makes its brain system different. And this is actually where we sometimes need to connect TVB with spiking networks. Because, as we said, TVB is this, a brain network model, quite homogeneous, very good to connect structural with neuroimaging data, but at the same time, a big part of computational neuroscience is all about modeling specific systems, for which we have very detailed information on what kind of neural populations exist, how they are connected with each other, etc. And such systems are modeled by spiking networks. So networks of spiking neurons where we are at a different level of detail. Each model there models a specific neuron, either as a point neuron, as again, as an approximation that a neuron is just a point in space, or even we have multi-compartmental models where we also model how the signals are transmitted along the axons and the different parts of the neuron. There are many simulators that can do that, can model and simulate neural networks. 3 of them that we have incorporated in the toolbox I'm going to show you is Nest and Anarchy. These 2 model only point neurons, and NetNeuron and its interface with Python, NetPine, that can also model multi-compartmental neurons. So in co-simulation, what happens is that we model most of the brain in TVB, and then specific regions that implement a specific system we need to model in more detail, we model as spiking networks. And then we have to have the 2 models working together, exchanging data in real time. And in order to do that, it is important to have an interface between the 2 at what we would call the mesoscale level. This is the level of populations of neurons, of millions of neurons that form a population or a specific network that we can describe statistically. As we already said, TVB, state variables, describe the average dynamics of such populations, like the average firing rate, what's called mean firing rate, or the mean potential, etc. At the same time, such statistical descriptions of neural networks we can also compute for spiking networks. Therefore, at this level of populations, we can have a link between the 2 levels of description. This means that our model has to have a clear mapping between state variables of TVB and populations of spiking neurons or spiking networks on the other level of description. And at the same time, since we are on a model of the whole brain, each such population has to be assigned at a specific brain region. So these are some constraints of the problem. And let's see now a little bit how we can make this work. And maybe I need to say a little bit words more about the why. So, okay, we are saying TVB is a quite homogeneous model, no much differentiation along the brain network. This becomes specifically a problem with subcortical structures, because subcortical structures do not really obey this abstraction of a neural seed that is more or less homogeneous. But instead, each one of them has a very specific structure in space and also in terms of connectivity. So we can think of scenario where, for instance, we want to place a system within the context of the whole brain, in which case we want to have this, for instance, a neural system for visual perception or for memory construction or whatever. We want to place it in the context of the whole brain so that this system receives inputs from the rest of the brain that are spatiotemporally specific, so that inputs from different kinds of the brain have different dynamics and are, depending on from where they're coming, they're different. So this is the case where we are really interested in one direction, from TVB, creating a context of the whole brain towards a spiking network. But in most cases, and when this is more interesting, is when there is really bidirectional connection. And we can think of 2 scenarios, like when the loop from the whole brain input to the specific dynamics of a specific system, we're modeling a spiking network, and then back to the mean field of the whole brain, causes effects that we cannot study otherwise, Like, for instance, if we need the cortex as the intermediary between two different subcortical regions, like there is an ongoing project that actually we're just starting it, where we want to model basal ganglia interacting with the cerebellum through the cortex, right? And through the corticothalamic loops. So it's really this second scenario where there is bidirectional interaction that is more interesting to us. But another important thing I need to tell you before we go further is that the two directions are not equal in the way they work. On the one direction, let's imagine now, from now on, we're going to denote all regions that are modeled in TVB as mean field models with n prime, as you see here, while when a node is modeled by a spiking network, we will denote it with n. So from TVB nodes to spiking networks, what we implement really is a coupling, because if some regions are modeled in TVB and some others in spiking networks, obviously we have to send input from the nodes from TVB towards the rest that are in the spiking network. In the other direction, however, it doesn't work like that. In the other direction, and this is because even the nodes that we model as spiking networks, they still have a reference in TVB in terms of where in the brain they are. Like what I said before is that we have a whole TVB connectome here, and some of these nodes might be implemented as spiking networks, but they still form part of the whole TVB brain network. So the way it works is that what we're doing in the other direction is that the activity of the spiking networks of a node N, of a region, brain region N that we're modeling as a spiking network, is transformed into mean field activity through some statistical transformation and goes and updates the state and the past states, actually, the history of the same node in its representation in TVB. Like what this would look like is that if this region, for instance, is modeled as a spiking network, it has some activity in time, which we convert to mean field activity. And at every point in time, we go and update it in here. And once this is done, for the rest of TVB, this node is just one of its nodes. It doesn't have any more difference. And this is then how this node couples to the other. So first, this activity is updates the corresponding region in TVB, and then this region is treated by the TVB model like any other region. So coupling takes place then inside TVB. So these two directions are different then. On the one hand, it's coupling. On the other one is an update. Let's see how this can work. So for the coupling, we have two scenarios. In one case, we can imagine that, let's say we have all the regions that are modeled in TVB, and they have some state variables that are characteristic of the mean field models they're implementing, like, for instance, average firing rate or average synaptic activity of a region. And now this activity has to be transferred to the spiking network in order to act as a coupling input for the regions that are modeled in the spiking network. So what we can do then is that for every such node that is modeled in TVB, we can extract this activity in time, transform it to become from average mean field activity to total spiking activity. For instance, a common transform is to take rates and generate spikes, okay? And then take this activity and somehow inject it as an input to the spiking networks. For that, we are using this concept of a TVB proxy. So what is a TVB proxy? It's a kind of stimulating device. All spiking simulators, one way or another, implement some kind of device that can stimulate the neurons. And this stimulating device is mapped to the specific TVB region and specific state variable that needs to be transformed and communicated. And it gets fed up with activity from TVB and injects it to the target TVB regions. So for instance, if this is mean activity, we take it through a transformation and it's converted into spikes. And then these spikes are given as input to this TVB proxy. We use the word proxy because it's a proxy of this node, right? It's the proxy of the N prime node. And these spikes then are sent towards the target populations of the spiking network node. And notice that this is done with connections that have a weight and time delay that is taken from the TVB connectome, because this is like a node, a region of the brain connectome of TVB. So just to go back here, again, if this is a mean-field node and this is a spiking node, we need to take the activity of this node, convert it into spiking activity, and send it to a proxy node of this, of this node inside the spiking network to generate spikes and send them to this node, but the two are connected with some weight and some time delay. So this weight and time delay is respected here. And we practically, in that sense, this TVB proxy node is like the TVB node inside the spiking network. In that case, as you can see, we have some advantages that we represent the TVB network inside the spiking network. We're respecting all the weights and time delays. And for instance, we can implement here some synaptic plasticity rule, for instance, right? We can have synaptic plasticity on these connections, taking advantage that we are on a spiking network model. But there is a disadvantage that if there are 100 nodes in TVB, we need one proxy node for its TVB node that sends activity to the spiking nodes. So this is kind of computationally more expensive. The other way is to actually, instead of sending the input of every TVB node separately to the spiking nodes, what we can do is take advantage of the fact that TVB anyway computes the coupling towards every node. If you remember, I will go back. There is, for every node here, it gets inputs from all other nodes. So this coupling with its delays is actually computed anyway for every TVB node. So what we can do is pre-compute the coupling for these nodes that are in the spiking network, just for any other node, and send the final coupling to be applied to this spiking network node just in time, the time exactly that it would be needed for computations. In that case, again, this coupling, which is computed as a mean field quantity, needs again to go through a transformation from mean field to spiking activity. And then again, we need a device acting as a TVB proxy to send this activity towards, to stimulate the neurons inside the spiking network. Only this time, we need one proxy for every receiving node, because it's really the coupling towards this node that is communicated. Also, given that this coupling is already computed with the weights and time delays that are determined by the TVB connectome, we don't need any further weighting or delays here. So we're just going to send the activity as it is. Now, the advantage here is that we need much less proxies. We need one per receiving node instead of one per sending node. But we have lost now the specification of one-to-one connections, right? Here we have a many-to-one connections now. So both scenarios are possible and both are implemented in the software toolbox I'm going to speak about, but still they're quite different. Mind that this transformation and the kind of quantity that can travel from the TVB to NEST can be practically any kind. Obviously, the most obvious transformation is when we convert mean field activity into spikes. But there are also examples where we just send currents, for instance. And also when we make a transformation from rates to spikes, it doesn't have to be that this transformation takes place outside in the transformer. What we can also do is send rates directly here, because usually spiking simulators have their own devices that are initialized with rates and can generate spikes. So there are many, on the technical side, there are many solutions here, each one with its advantages and disadvantages. Yeah, but both is possible. We can generate the spikes with our own algorithm and send spikes, or we can just send rates and generate spikes with the devices that every spiking simulator has available. Now, in the other direction, as we said, we need to update the TVB activity of node N with the spiking activity of the same node. Since this node that is implemented in the spiking network, it's still represented in the TVB network. So this is kind of more straightforward. We need for every population that has a mapping to a state variable on the TVB side, we need to record its activity. So again, we need a proxy for every such activity. Like if, for instance, in the Wilson-Cowan model that I showed you, which is going to be our example for today, we have a state variable for the excitatory population and one for the inhibitory population. And let's assume that also the spiking networks we're creating in the spiking network model also have an excitatory and an inhibitory population of neurons for every brain region. So it is the excitatory activity that we need to record, transform it into mean field activity, and go and update the TVB state variable. And similarly, we need another proxy to do the same for the inhibitory population. So in these cases, the TVB proxies are actually recording devices, and we need one for every region we have in the spiking network. And again, usually this transformation is from spikes to rates. So we need to form a histogram of spike timings and convert them into some kind of instantaneous mean firing rate. But again, this could also be done by recording currents, for instance, which is also possible. Or any other activity, even potentials. But it's true that the most common use case is where we are actually recording spiking activity here and we're converting it into rates. So this is most of the science behind this co-simulation and the interaction between the two scales and the two kind of models. Another important issue is that we need to, as you see, we need to exchange simulations on the two scales with exchange of data. And this means also these exchanges have to happen at specific time points. There has to be synchronization between the two scales. So, and there we have again different options. So what we started with while learning and trying to implement this is to the simple case where we simulate TVB for a small time step. We send data to Nest or to whatever spiking network. Then we simulate the spiking network, and then we send data to TVB. And a good rule is, since spiking networks we work with discrete elements like spikes, it's better if we have a smaller time step. For instance, usually we choose a time step for the integration of the spiking network that is at least half the one of TVB. And yeah, so we simulate TVB one step, we simulate the spiking network for one step, which is actually two, etc., and we exchange data. But this obviously needs a lot of instances of synchronization, and it can get very slow. The next improvement of that is that given that we have time delays between brain regions, we know that every node needs coupling from the other nodes with some delay, not instantly. And we know that from all the interactions in the TVB network, there is some minimum delay. So nodes, and we can use this minimum delay, which can be a few milliseconds, right, as the synchronization time, so that we decrease how many synchronizations we need to do. And this is what you see here, where still we have a serial situation, simulation, sending, simulation, receiving, simulation, sending. But now we only do this synchronization every minimum delay of TVB. What we are working right now is to actually go one step further and have these processes parallelized so that we exchange data, we simulate the two simulations at the same time, and then we exchange data, and then we simulate, and then we exchange data, so we can save time by having the two simulators, TVB and the spiking network, simulating at the same time. And lately, what is our last development we're trying to implement is what if the transformations take also a lot of time? Because you saw that we can generate spikes in the transformation, and we need to convert spikes into rates. And these computations can also take time. In that case, we can also try to parallelize not only the two simulators, but also the transformations. And in that case, we need to we gain time, maybe, by parallelizing the transformations as well, but we need to, in this case, synchronize every half minimum delay of TVB, right? Because we need to spend half time to simulate and half time to send for the transformation of the data. So these are a few details of importance, because synchronization is very, very important so that we can have co-simulation in real time. Now, all this is implemented at a software toolbox we call the TVB Multiscale toolbox, and you can find it in GitHub. It's open source. You can download it, you can use it, you can contribute if you wish. And given though that for this toolbox to run, there are several softwares that all need to be installed at the same time, TVB, 3 simulators, some other software. We also have some Docker images implemented and available, such that you can create the environment easily. A few words for this software so that it's easier for you to use it or understand it and further develop it if you wish. There are several components in this software, all of them are implemented at different classes, Python classes. First of all, of course, we have the TVB model and co-simulator. Then we have whatever has to do with the spiking network model, and which means that we had to program for several classes that wrap around the neural networks, so that we get two advantages out of this. One is that we can have all neural networks having an association with the population label and the brain region of TVB, which, as we said, is very crucial for the whole thing to work. And secondly, so that there is some user interface, some API that is very similar, no matter if we are co-simulating with Nest or with NetPine or with Anarchy. And similarly, we need to have some classes that implement the TVB proxy nodes inside the spiking network, either as devices that generate spikes or as devices that record. So similarly, this is part of the model on the spiking network model. And then we also need classes to send data or to transform, to implement transformations like from rates to spikes, spikes to rates, or symbol scalings if it's current to current, etc. Finally, what we call an interface is something that combines communications and transformers, and it is attached to TVB or model or the spiking network. So we have the TVB model, the spiking network model, and between them we have interfaces, and these interfaces are like pipelines comprised of communicators and transformers. You can see all this here because this all has a very modular architecture. The idea is that these classes can be combined and form different workflows in a very modular way, and also working towards parallelization such that different combinations of those can work in parallel on different processes. For instance, if the transformations we are doing are relatively fast, then usually the bottleneck of the co-simulation is the spiking network. This is what can take a lot of time. In that case, it might make sense to draw a line here and have everything related to TVB and the transformations implemented in one process that would work in parallel with everything that has to do with the spiking network. But if instead we generate spikes or we receive spikes and we have to compute rates and these spikes are millions or whatever, then these computations can also take time. And then it might make sense to have TVB, the two transformers, and the spiking network all being on a different process and all working in parallel. In that case, we would have to build different interfaces. So the whole thing is very modular and can be assembled in different ways, while the science remains pretty much the same. And similarly, for each one of these components, in order to help the user configure them and build them, for each one of the classes of these components, we have a builder class, as we call, and we have informative builders and non-informative builders. So informative builders actually implement a model. So the best way to make a model and store it so that you can use it is actually to program a builder. So we have a builder to configure the TVB co-simulator, or to configure the spiking network, or to configure the interface, etc. And then there are also higher order classes that we call apps. There are TVB apps, spiking network apps, transformer apps, and they can all be orchestrated by a higher, even higher order class called an orchestrator. So an orchestrator implements a whole workflow. The usual workflow, let me go there. The usual workflow has to do with setting up some configurations, then configuring first the TVB model and simulator, then configuring the spiking network model, then building the interfaces between them, then simulating, and finally there are also tools to gather results, analyze, plot, etc. So an orchestrator actually uses apps, the TVB app or the spiking network app, and it can formulate the whole workflow in a few lines of code. So these are aspects that can help the non-expert user, I would say, but I'm only referring to them because in the notebook, we're going to go into more detail and actually see each one of these steps. In the end of the day, though, what we are really trying to do is to have the gist of the whole process as simplified as possible, because of course you have to be an expert user of TVB to be able to implement the TVB model. Of course, you have to know how to make the spiking network model in one of these three spiking simulators we're using and we are offering. But in the end of the day, the whole toolbox is meant mainly to configure the interfaces between the two scales. And this boils down to being a configuration in terms of dictionaries of properties, as you see here. So the user can define as many interfaces as he wishes between the two scales for the one direction, from TVB to the spiking network, and from the other direction, for the spiking network to TVB. Each interface is configured as a dictionary of properties. And those properties are some very basic ones that you cannot avoid putting in. The main thing is that the mapping is necessary, as we said, between the state variable of TVB and the population label for the spiking network. We need to tell to the interface that, hey, you need to take the rate of the mean field and somehow send it to this as a coupling input to these populations in the spiking network. And then we need to define a model. What should that quantity be? For instance, if you say that this is a rate, it means that we're going to send rates. but it could be also currents, or it could be spikes, in which case you would have to generate the spikes in the transformer. And then one needs to define or parameterize the actual transformation function and the TVB proxy that is going to be implemented on the spiking network side. But the good thing is that once this mapping is done, the basic model is chosen, then there is some code in the builder of the interface that will go to default options for the proxy and the transformer function. So even if you skip these inputs completely, something will come up. On the other direction, from NEST to TVB, it's also the same thing. You need to say from which population you want to record and which state variable you're going to update in the TVB side. And then, given that here by default, we assume that we are recording spikes, all other inputs are actually also a little bit automatically chosen unless we place some configurations like this in the dictionary. And as I said, we don't need to have the same interface between every pair of nodes. It could be that we want to have a different way to transform rates to spikes, for instance, if the input is coming from the visual cortex towards the cerebellum, let's say. Imagine the cerebellum is whatever, modeled in a spiking network, and we want a different interface between some cortical regions and a different interface for some other cortical regions. Then we could define several such dictionaries, and then the builder will create different interfaces. But in the end of the day, usually it's a code like this, not many more lines, in order to define these interfaces. So, yeah, I will not go into more details on the software. The best sources now to work with it is the ones I showed you and the ones we're going to see in a while. There is a collaboratory in eBrains with some information and all the resources and instructions that if you follow them, you can run the toolbox at eBrains Jupyter Lab. This is a nice way to start working with it and get accustomed to it. And this is what we're going to try to do today. But obviously, as I said, you can also get the tool from the Docker Hub, and or you can build the Docker image yourself also. Before we finish this first part, I will talk also for some first applications in real world studies we are conducting right now, to also give you some examples of eventually where this tool has been proved to be useful. So one study that we're in the process of finalizing is one where we study the effect of the cerebellum in modulating the coherence between the motor and sensory regions of mice that are freely whisking during a freely whisking condition. So what was shown is that if you deactivate the cerebellum, the coherence between motor and sensory regions drops. And obviously you see here that as there is a subcortical structure with a very specific connectivity that modulates an activity between two cortices, this is where really a whole loop of activity has to be implemented. And this is why we need, on the one hand, the cortical model of the TVB brain, and at the same time, a more specific spiking model of the cerebellum, and having the two interacting. As I said, there are also being developed, this study was with interfacing TVB with NEST, but at the same time, we are working with interfaces with NetMine. NetMine is a Python toolbox that makes it easier to use Neuron. And Neuron is actually the most widely used and complicated spiking simulator because it can implement multi-compartmental models. So we are working on first examples, but we haven't yet published anything on TVB NetMine. But in any way, what is important here is that we can actually have a model that goes from the whole brain down to multi-compartmental neurons. Finally, there is the third simulator that we are interfacing to. It's called Anarchy. Anarchy is very different to other simulators. Most of the simulators implement a model of every neuron separately as a separate class, and then they have some way to have them communicating. Instead, Anarchy is a lot like TVB. What it does is that, again, you can implement neurons with different models and connect them, but in the end, Anarchy will compile everything to a big chunk of differential equations, just like TVB in the end is a big set of differential equations. It will compile it to C language, and it will run the simulation very fast. So the advantage of Anarchy is that you can very easily write code you can write equations, in other words, of the neurons, and then you can connect the neurons yourself, and in the end, in the background, it will compile everything and simulate it very fast. So it's very easy to add your own neural models here without writing any complicated code in C or whatever. And we have used the TVB Anarchy interface for the first study we published with the TVB multiscale co-simulation. This was a case where we modeled virtual deep brain stimulation for the spiking basal ganglia model. I will not go into details of the study. I just want you to briefly show you how it looks. In this study, we modeled the whole brain and specifically the cortex in TVB, while we had a more detailed and complicated model of the basal ganglia with different populations and their specific connectivity. And what we had was, so we had a co-simulation of this network. And what we showed in the end is, and we also modeled stimulation at some of these basal ganglia populations. The reason was that we wanted to show how the basal ganglia deep brain stimulation can improve between control and patient resting state activity. What you see here is that we managed, so we had we modeled a control patient, a control subject network, and a patient one. And originally we could have the effect where thalamus fires less for this kind of pathology. And then we showed that by stimulating, thalamus was rectifying its firing rate towards the situation of the control subject. But given that we had the network connected to TVB, we also got the different networks that get activated for the whole brain once the DBS, the deep brain stimulation, deals with this inhibition of thalamus. So anyway, I will not go into more details here, but this study is published and you can find it online. So yeah, these are some references. I will send you the slides anyway. Some references for this study, and I will stop by just saying that there is a lot of work still to be done with this tool on all aspects. On the science aspects, we need to compare and validate the different ways of coupling between the two scales, the TVB mean field models and the spiking network more detailed models. We are still working, as I said, with parallelization and optimization of the co-simulation to make it faster. There is a lot of work to be done on the software side in terms of improving documentation, test coverage, etc. But at the same time, as you see, there are several studies running that use the tool. So if any one of you wants to contribute in any way, please feel free to contact us. Right, so I suggest that I have a look at your questions now. I will, let's see how I can do that.
We get one really interesting questions considering the capabilities on the lower scales, considering also glia cells. Maybe you can refer to that.
Yeah, from the tech, so I'm not an expert on that. I don't know exactly how glia cells are modeled, but I know that from the technical side of it, there is no limitation. So if you have a spiking network simulator, Nest, Neuron, or Anarchy, and you can build a model of these cells and connect it to the other neurons, from the perspective of co-simulation, nothing changes. So in other words, yes, we could have a model that also includes glia cells. I don't know if this answers the question. How about making a 5-minute break and be back at 5:35 or so? Okay. Okay, I see happy people. So let's be back in 5 minutes and we're going to go through the notebook example. Great. So as I said, our starting point is the eBrains Collaboratory. This is public. You don't need to be registered to eBrains to see it. It's the main reference for resources. And in case you wanted to run yourself the tool, I hope that you have already followed the instructions under this paragraph so that you run the toolbox at eBrains Jupyter Lab. What needs to be done is the tool is already installed there, but the examples are not available. So one has either to download the specific folders with examples and documented notebooks and then upload them on the platform. Or the other option, which I prefer, is to do what is called JIT sparse checkout from the JIT repository, in which case one can clone only the folders with examples. This is what I have done. So, and then you have the notebooks there, and we can run them and we can modify them because there is persistent storage there for every user, which means you can log in, do your work, log out, and then log in next week, and your work will be saved and you can find it there. So if we press here for eBrains Jupyter Lab, and we can select one of the two available supercomputers, and then you can register with your eBrains credentials as registered users. And in this case, if everything works well, maybe the first time you log in, it might take some time. You might need to retry it because the first time a user is connecting, I think it has to build several things. So you might need to retry or whatever, but eventually you end up with on a picture. Well, I will close this, something like this. There are different options for you to start a console or a notebook with a different kernel. What we want is, in the end of the day, in my case, I have downloaded the examples here, and inside I have a folder for docs and one for examples. The notebook we're going to work with is in docs notebooks. It's called TVB Nest Wilson Cowan. And if you double click, it will open. And you need to also set the kernel, preferably to eBrains Experimental, just to be sure it's the latest version there and the tool is installed. That's all. And in that case, hopefully you could run the notebook yourself. So I'm getting into it. I will not go into every single detail because first we assume that you have already tried to configure your own TVB simulation at least once. So I will go through this quite fast. And second, unfortunately, we have to assume that you are a bit accustomed to how Nest, in this case, because it's Nest that we're going to use, how Nest works and how one can configure a simulation, a spiking network simulation with Nest. If not, it's not a big deal, because I will just go through the main aspects of that. And then I will try to spend more time on how we configure the interface between the two tools. So in this node, we implement a scenario where all nodes are modeled in TVB, except for only 2 nodes that we just chose randomly. And we implement them in Nest as spiking networks. The TVB model is the Wilson-Cowan mean field model. So at every region n prime of TVB, we have these equations working out. I already showed you this model. It assumes an excitator and inhibitory population. The state variables have the meaning of some kind of dimensionless or synaptic activity or something like that. The values usually go from 0 to 0.5. So they're not directly convertible to firing rates. Actually, in this model, they are convertible to firing rates only after they go through a sigmoidal activation function, as you see here. And there are several connections implemented. Its population is connected to itself. And also they are connected one with the other. There is an excitatory connection from the excitatory population to the inhibitory one, and the inhibitory connection from the inhibitory population to the excitator. So we're going to build a similar spiking network at the 2 regions that we're going to model in Nest. So the workflow starts with several basic configurations. Here I have implemented these configurations as capital letters choices to be used later on in the notebook. Like, for instance, choosing TVB Nest means that we make a co-simulation, unlike if we choose TVB or only Nest, in which we're going to simulate only one part of the network. Nest model builders, since this is a model I have already implemented, there are both opinionated and non-opinionated builders that can generate the neural network. So I will show you this, what it means in a while. And some of the parameters that choose how many regions are totally in TVB and which regions are going to be modeled in Nest. So we just choose the 2 first ones here. How many neurons its population will have. This will affect how fast your simulation is going to be. And then there are very basic choices for the interface between the 2. As I said, we can implement models where what we are sending from TVB to Nest is rate or spikes or even current. It will work in all cases. You can try all 3 of them in this case. And also a big choice is whether we implement the scenario where we compute coupling in TVB and we send Nest to Nest the final coupling that is going to be used, the final coupling input, or instead, this is the choice where we have TVB coupling, or instead we send to Nest the activity of every TVB node, and the coupling is implemented through the connectivity inside Nest. We're going to see these details also. And finally, there is a final constant here that you will see that scales up and down the strength of the TVB to Nest coupling. The rest of the choices are not so important. Only what is important to run this notebook is to set this path here. I will copy paste it in the chat also. If I manage to access the chat. Yeah, great. Because as we don't have the data at the same location, we need the data are actually inside the folder examples data. So I assume that you have already uploaded everything and you can find it at this path. This is the data that is necessary for the TVB model. So anyway, this is what we do here as a configuration. And then the first step we need to take is to actually prepare the TVB model. And preparing a TVB model means to choose the mean field model, in our case, Wilson-Cowan model. And we need to choose the connectivity, which we load from this file I just showed you before. And inside there, it will have different elements. I hope you have seen that before in the previous classes, like the locations of the brain regions in space, and mainly, though, the two most important ones is the matrix of the connectivity weights and the matrix of connectivity track lengths, because this will determine the weights and the time delays of the connections. All other stuff is not so important, but these two elements have to be there. And in this case, in this data source, we have everything. So we need to create a co-simulator class here, which is a variation of the simulator class of TVP, and we need to define all these basic elements, the model, possibly with different parameters that we can change here, the connectivity. Then we need to choose a coupling function out of the available ones in TVP, and we just choose a linear coupling. And we need to choose also the integrator that will integrate the differential equations, the time step, and the amount of noise we wish to have. Finally, we can optionally determine the initial conditions for our simulation. And of course, we need to record the activity of TVP. And here we define just a raw monitor, as it's called. A raw monitor will just record the activity of these state variables, so the source activity, but in principle, we could also here record the EEG, MEG, fMRI, etc. So this is the main steps, very fast, of how to prepare a TVP model. It's only a few lines of code. We just say simulator configure, and the simulator is ready to run. Here we are also taking one more step. We're creating a serialization of the simulator. So several of these properties are actually populating a dictionary and saved to a file, because they're going to be used for later on to build the spiking network and the interfaces. And here we have a plot of the connectivity matrices. First, the weights. So you have all regions here and the strength of the weights of the connections, and also a matrix of the track lengths. And several printouts that I'm not going to go through. Okay, so as I said, the scenario we're going to build is that two of the regions have to be implemented as spiking networks. And so one region, two regions, and for each one of them, we have an excitatory and inhibitory population similar to the mean field model. And we can, for instance, place 100 neurons to each one of them. And we need to implement all these connections, the self-connections of each population, the connections between the populations within a region, as well as connections between the two regions that are in the nest network. So this is what we need to do by creating a nest spiking network model. We just choose here one of the simplest integrate and fire neurons that nest has available, but any other neuron could also work. And now there are three ways to build this network, depending on how good experts we are of the nest simulator. One way is that I have already implemented this model into a builder. So there is already a class that can be loaded, maybe a bit further configured. And then we can just say to the builder, configure, build, and the spiking network will be built. Because I have already implemented that. This is what I call an opinionated builder. The code I have put into the file where I have made this opinionated builder is actually the same as in the case of loading a non-opinionated builder, so nest network builder, not a specific model, and populating its different attributes with configurations. These configurations have to do with the populations we want to create at each brain region. So there are properties to give a label, to choose the neural network model. We said we're going to use this one. Parameterize it, possibly, if we want. Scale, which means that each population will have n neurons times the scale. So if we wanted to have some populations with 150 neurons and some with 50, we would have scale of 1.5 and scale of 0.5. But we could, at the same time, scale all populations up and down by just changing this property here, the population order. And what is very important, select where in the brain, out of the ones we have decided to implement a spiking network, we want these populations to be implemented. Given that we want all populations to be implemented in both the regions, so we have some kind of uniformity here, we are not setting this input, and therefore these populations, an excitatory one, an inhibitory one, will be built in both regions that are built in NEST. So this first configuration determines the kind of populations and where they're going to be built, how many neurons, what model, etc. Similar configurations as lists of dictionaries are implemented for the connections within its region and between populations. So the connections you see within each one of its regions. So for every connection, we need to define the source and the target population. So it's, for instance, a self-connection of the excitatory population is starting from population E, going to population E. We need to define the synaptic model. We need to define a dictionary of properties that is specific to the NEST simulator, saying what kind of connectivity, like all-to-all, one-to-one, or random, we should have between the populations, and we should define some weight and some delay for these connections. And there are neuronal models that can have different receptor types for the synapses, and therefore we would also have to define the receptor type. So most of these inputs are specific to NEST, but they have the corresponding attributes in other simulators as well. I won't go into more details because we don't have time. But yeah, the idea is that its kind of connection can be determined by dictionaries of properties like this. And again, we need to say if a connection needs to be implemented in all the brain regions or in some selected ones. Again, here the connections are the same for both regions, so we don't populate this input, we just leave it to none. And there are 4 connections we're building: self-connection for excitatory, self-connection for inhibitory, connection from excitatory to inhibitory, which has a positive weight because it's excitatory, and connection from inhibitory to excitatory with a negative weight because it's an inhibitory. And this is how we configure the connections within its region. But then we also need to configure connections between the regions in a similar way. So again, we need to implement to determine the source population and the target one. So here we're saying that activity of the excitatory population of one region will target both the excitatory and the inhibitory population of the other region. And this is indeed how the model works also for mean field, because if you look at the equations here, both the excitatory and the inhibitory population receive coupling input from other regions' excitatory activities. So we're doing the same for the spiking network as well. And the other inputs are similar, but there is now a difference. Since this is a connectivity between regions, we need to respect the weights and delays as they come from the TVP connectome, right? Because these 2 regions are still part of the TVP connectome, so there is a weight and delay determined by TVP. So we define some functions here that take as arguments the source node and the target node in dice, and they can get this information from TVP connectivity weights and delays matrices. Finally, it's not necessary that all connections would be uniform around the brain. We could define many such connections and just make sure which source and target nodes should be applied. But in this case, that we have only 2, and these 2 the connections in both ways are going to be the same. So again, we're not changing this input. Finally, we might want to define some devices for the spiking network to record activity, like a spike recorder recording spikes, or a multimeter that in Nest records continuous variables like currents, potentials, etc. And we can assign each one of them to one of the region and populations we are recording with specific labels. And at the same time, it could be the case that we want to also create some stimulation devices that will have some background activity and send it to each one of the populations. So here we're also defining input devices, and we're sending a constant stimulation to the excitatory population of each region with a constant firing rate. So they send spikes. All this is not obligatory, of course, but it's something that one can use the builder to configure. And then again, we'll say builder configure, builder build, and we create a class that is wrapping around the Nest network model. So no matter if we use the opinionated builder or if we configure the builder ourselves, in the end, these two lines will build the builder. But as I said, if we are expert users of Nest, we don't need the builders of TVB Multiscale toolbooks. We can just use Nest code ourselves and do practically the same things the builder does when it builds, but ourselves. Only in this case, it's us that we need to take the Nest classes and wrap them inside the TVB multiscale classes for population, region node, brain, network, etc. So for instance, this first loop here is creating the desired populations using a Nest command called nest create. And then it's assigning them into the correct place, into the Nest network class, with the correct region name and population label. Similarly, later on, we are building the connections within its region or between brain regions using the Nest command connect. But I will not go into details, or we can actually build the Nest network devices by, again, using the nest create command. So it's exactly the same stuff, only this time we don't do them in the background, but we explicitly write Nest code. So there are these three ways eventually to create the Nest spiking network. Again, in all cases, in the end, we need to configure the network to prepare it for simulation. So until this point, we have built the TVB model and the Nest model. Now we need to configure and build the interfaces between them. And this is where I want to spend some more time. So similarly with before, we need to configure a builder to do that. And again, one can use opinionated builders where all the configurations are preset. I have a builder for this model, but here we're interested in to see these steps one by one. So we implement a non-informative builder, which we're going to configure right now. So the basic configurations, since everything runs on the same process here, it's not a parallel co-simulation, but a serial one, everything runs on the same process, so the builder can have direct access to both the TVB simulator and the Nest network. So we assign them here, and then we configure the basic model that we want to use for sending data from TVB to Nest. And you saw this configuration at the first cell of the notebook, so we have chosen rate for this example. And also we set these flags to true so that the connectivity is bidirectional. So input flag true means that there is input from Nest to TVB, an update. And output flag true means that we're going to send data from TVB to Nest, so that we need to build these interfaces. Another very important option is to choose whether we're going to be sending directly the TVB coupling to Nest, or whether we're going to be sending activity of every TVB node separately. If you remember, these are the two scenarios we're having here. And which we can make here a bit more specific because, the first scenario is where we take the activity of every TVB node and prime of the excitatory node, because if you remember, it's the excitatory node that goes from one node to the others, and take it through some transformation. For instance, if we need to take this activity that has a value between 0 and 0.5, scale it somehow to become something like a rate. And then if we are sending rates, because we said we're choosing the model rates, we need to implement in Nest a device called inhomogeneous Poisson generator, which is feeding, to which we are feeding rates instantaneously. And then this device uses a Poisson random process to generate spikes inside Nest, which in the end of the day will go to the target excitatory and inhibitory population of the two nodes we have in Nest, using weights and time delays that we are specifying here based on the TVB connector. This will need one such proxy device for every sending node. Alternatively, if we compute already the coupling for these nodes inside TVB, we're going to be computing this coupling in terms of activities. So it's going to be an activity coupling. We will have again to take it through transformation to become a rate, and then feed it to a device, the same device, an homogeneous Poisson generator device, to generate spikes and direct them towards the targets. Only this time, this input is already the coupling that needs to be applied directly to these populations here. So we need only one such device for each one of these population and for each of the regions. We have two regions with two population each, so we're only going to need 4 such devices, 4 such proxies. So these two scenarios are implemented, and we can run either of the two by just tracing this input. The default is to use TVB coupling, which is faster, which is this second scenario where we are setting directly the TVB coupling, and it is we only need 4 proxy devices. So this is decided here. And then there are some additional inputs that are needed for the interfaces, mainly the nodes, where the specific indices of the nodes that we model in Nest. And finally, yes, there is another flag that is quite important. This is telling to the interface manager, let's say, that the nodes that we implement inside Nest, so these 2 nodes, are implemented exclusively in Nest, which means that TVB, we are not caring at all to simulate them in TVB, and therefore we should cut the connections TVB has between these 2 regions. They're only implemented in Nest. This is what exclusive nodes means, and by default we set this to true. It could be the case that we assume that we're modeling in Nest only a subpopulation of these regions, which otherwise keep existing in TVB and being simulated there, in which case this flag would be false. But again, the default is to have it true. And the important thing here is that we have these 2 configurations for the output interface and the input interfaces, which we initialize here as empty. And it is exactly this that we need to populate now with configurations in order for the builder to run and build the interfaces between the 2 scales. So the basic, I'm not going to too many details, but the idea is again that, as I said before in the example with the slides, we have to configure its kind of an interface as a dictionary of properties. And some of them are very basic and cannot be missing. Some others we can code with only 1 keyword, or we can go even into more detail in this configuration. So the minimum information is that we need to say that we want an interface from TVB to Nest, right? From the state variable of the excitatory population in TVB, and target the, that's a mistake here actually. yeah, we should be targeting both the excitatory and the inhibitory population of the, yeah, it should be like that actually. But it's never too late to correct it. It should go to both the excitatory and the inhibitory population of the every nest region. And the other very basic input is that at least we need to say what kind of model, what is the quantity we're sending? Is it rates? Is it spikes? Is it current? And this we have configured above as rates. Now, in principle, we could stop here. With these three inputs, even if we had nothing else here, the builder could build the interface because we have already given defaults both for the coupling mode, which said we want coupling to be computed in TVB. For the proxy indices, we have already initialized them up here, if you remember, as to be equal to the nest nodes. But again, here we could actually differentiate them so that if we want to have many different interfaces, they correspond to different combinations. The proxy model is the kind of device we are actually implementing here. So given that we want to send rates, the choice is actually by default. We cannot do much. It's in an inhomogeneous Poisson generator we have to use. And therefore, that's why we don't give any more information here. We could also comment this out and nothing will change. But in other cases, for instance, if you were setting spikes, we could have, no, again, we could have only one option. So this input is not so important. Similarly, for the transformer model, so what kind of transformations we want to do, it's also an easy choice in this case because since we're just sending rates, it's only a matter of taking a rate value, which is a scalar value, and somehow transforming it to some other rate value. Of course, a more accurate modeling here, look at the model. The original model here, it takes activities, it takes them through a sigmoidal to make them rates. So ideally, we should also build a similar sigmoidal function here as a transformer. We have done something like this in other cases. Sorry, let me find it. It's down here. So we could have built a transformer class with this sigmoidal function, but for the moment, by default, it will just use a linear transformation that just scales up and down the activity in order to convert it into a rate. So these inputs also could be missing and it could be directly initialized with the basic model. And finally, we need to say towards which nodes this interface should target, but again, this will be the same as this. So also this input is not fully necessary. So really what is very basic is the mapping between the state variables and the populations and the kind of model, because this helps initialize everything else. In other cases, it's not that simple. Now, there are also additional inputs we might want to further configure, like, for instance, I said that we're using a linear transformation here. We're just taking this activity that has values between 0 and 0.5, and we need to convert it into some kind of rate in hertz, right? So that requires parameters like, yeah, in the case of rate, we're here. We need to scale this to some value. We need to make, for instance, 0 to be 0 rate, 0 hertz, and 0.5 to be some maximum rate, like 100 hertz or something. So we need to scale it. So we're just defining here some scaling constant. And that's pretty much, so we define this as transformer parameters. These are specific keywords that the builder can read in order to build the model of the interface. So, but what I want you really to keep here is just that a few properties like that are enough in order to build the interface. Now you see some if else here because I have implemented code to implement all possible kinds of interfaces using currents or using spikes. And you can change that if you go up here to the configuration, and you can choose spikes or current, and then a different part of the code will be executed down here. And I have tuned the weights such, you see that there are small differences in the scaling weights, such that in the end, the activity of the spiking populations in terms of firing rate is about on the same levels. So if you want to play with it on your own, you can just change some of these flags or change the values and see the effect in the end. So that was for the interface from TVB to Nest. From Nest to TVB, as we said, the situation is much simpler, or what we need to do is to define interfaces that record the activity of these populations, the excitatory and the inhibitory population, and they go and override this activity inside TVB. So again, the most important thing is the mapping, which is very simple here. The excitatory population will map to the excitatory state variable, and the inhibitory population to the inhibitory state variable. The proxy indices, again, are not really necessary, because if we don't put them, it will just apply the same interface everywhere. And by default, the proxy model we choose is called spikes mean. What this means is that we're going to have spike recorders in Nest, recording all the spikes of each population at any time segment. And it will take the spikes, it will scale them through the time, and it will scale them with the total number of neurons of each population to create an instantaneous mean firing rate. And actually, this job is, sorry, I was confused. What the proxy model will do is just to send the total number of spikes, and then it's a transformer model that will use a histogram to convert it to an instantaneous firing rate. And here, the most important parameter for the transformer is how many neurons we have and the scaling variable again. So again, we don't have time to really dig into all the options and the details here. Again, the most important thing is the mapping, and pretty much the rest comes as a natural choice or just a scaling parameter that you need to define in order to convert this spiking activity in hertz into a quantity between 0 and 0.5, because this is the range of activity that this Wilson-Kaman model has for the state variables. So similarly with the Nest network builder, the interface builder gets these interfaces from us. And then all we need to say again is configure. And in the end, we have a line to build the configuration and inform the simulator for these interfaces that have been just built. So finally, we have completed the construction of the model, and all we need to do is to say that we want to have a TVB Nest co-simulation. We need to configure both the Nest network and the simulator, and decide how long we want to simulate, and then just say, hey, run. And it will run. In this case, it ran for 1 second. It took about 15 seconds. And the last step is to just get the results out of it. I won't go into the details of that code because it's not so important. But the nice thing is that we can record the activity both on the TVB side. For instance, on these plots, you see time series of all the brain regions. And notice that the two first regions that are modeled in Nest have this very spiky time series, exactly because the instantaneous activity is following the spikes. And since we've made a model that is not random at all the neurons are the same, they have the exact same connections, they started with the exact same initial conditions, they're all the neurons fire at the same time. That's why you see a very spiky activity here for the first two regions that are modeled in the spiking network. This is a little bit made on purpose here to show the difference between the two regions that are modeled in the spiking network and the rest. Yeah, and here you see exactly the activity of the two regions that we model in NEST, still recorded in TVB. So you see they go from 0 to 1 because all neurons fire exactly at the same time, so they reach the maximum rate at the same time. Similarly, it's the same thing here. But also, we can record this activity on the NEST side. If you remember, we defined the spike recorders to record both spikes and continuous variables, multimeters, from the NEST side. So we can record it and plot it and compute all kinds of things. So here we have spike rasters. Let me zoom out a little bit. It's not possible. Anyway, for every region here, and on the y-axis we have neurons, and on the x-axis we have time, and there is a dot for a spike that is fired, and you can see that they all fire about at the same time. And this is why we got this very spiky time series in TVB. We can compute correlations between the regions. We can compute their firing rates for every region and population. And there are also a bunch of tools to record to compute measures of spike synchronization. I won't go into details for that, because really the focus of this is what I tried to describe in the last almost 2 hours, is that in the end of the day, the focus here is on the interface themselves. And so most of the work is implementing this one cell on the notebook. And the ideas I wanted to convey to you is how important it is to map correctly the activities of the one scale TVB and the other, the state variables of TVB and the populations of the spiking network, and how we can configure the different kinds of science we want to have behind that, whether it is a rate or a current or a spikes transformation. And with this pieces of information, we can actually interface between the two scales at the population level and have this co-simulation running. I will stop here so that we might have some time for questions. Let me also tell you that inside the same folder, there is an example using Anarchy and one using NetPine, and you will see the similarity of the code, because apart from the code that is specific to building a NEST network against an Anarchy or a NetMine network, everything else is pretty much the same. And if you actually use the builders for building the nests or Anarchy or NetPine network, it's even more the same. So there are 3 notebooks here with different implementations, and then there is another folder with examples, and there are further examples. Most of them are not so well documented because it's ongoing work in general. But yeah, there are a few more examples anyway. So I will try to see the chat now, if there are any questions.